Welcome everyone to NSTA web seminars where you can find live interactive learning at your desktop. Tonight's presentation is part of our NASA Explorer School series, and it's titled What's New in Planetary Science? A tour of recent discoveries in our solar system and beyond. Tonight's presenter is Sarah Noble. My name is Bryn Slate and I'll be moderating tonight, and Jeff Lehman is online with us to provide technical support. I'd like to remind everyone to visit the NSTA Learning Center, your online portal for over 10,000 resources for science educators. When you visit the Learning Center, you will find that over 3,500 of those resources are free, and you can use the My Library function to save them to access later when it's convenient for you. The community forums are the place for you to interact with your colleagues, other teachers from across the country and from around the world. And the online advisors are there to help you find the resources that you need. If you're looking for a way to organize and document your professional learning and reach your goals, do feel free to check out those free tools which will help you do that. And it's all available by going to learningcenter.nsta.org. And now I'd like to go ahead and turn it over to Sarah. She's a research scientist at NASA Goddard Space Flight Center in Greenbelt, Maryland. Welcome, Sarah.
Thanks, Bryn. I am very excited to be here. I'm happy to see so many people out, and it's fun to see where everybody's at and what you guys are teaching. This is going to be really cool. So this is my first time using Blackboard, so give me a little bit of a learning curve here, but I think we've got a lot of good stuff to cover. I've got a lot of material to cover. If I'm going too fast, I'm prone to doing that. Please let me know, and I'll slow down. We'll get through whatever we get through. So yeah, I'm here to tell you about sort of the new things in our solar system. Does anybody recognize the little character in the corner there? Am I the right anybody here of the right generation to recognize who this is? Oh, now I feel really old. So this is Interplanet Janet. She's the Schoolhouse Rock character that teaches about the planet. So just like she gave a tour through the solar system, I'm going to give you a tour. I thought I'd start with a little bit about my background. I was born and raised in Minnesota, went to the University of Minnesota, got a bachelor's degree in geology, and then I went to Brown University for my master's and my PhD, also in geology. I then took a quick break from the academic life and worked for Congress, always an interesting experience, for a year or so. And then since then, I've been pretty much wandering around NASA. I've managed to hit 4 different NASA centers over the last like 6 years. So hopefully I've sort of settled down now to where I'm at. But it's been kind of fun to sort of see how different NASA centers operate. At the moment, I'm at NASA Goddard in Maryland. I also spend half my time at NASA headquarters, which is where I am tonight, talking to you from my office at headquarters. So it's a really fun opportunity to see a lot of what is going on at NASA, particularly in planetary science. So I'm going to share some of that with you tonight. So the plan here is to sort of take you a tour through the solar system. We're going to start with Mercury and work our way out. I will not give every planet the same amount of attention because, frankly, some are cooler than others, and so I'm a little biased. You'll see more from some than others, but hopefully you'll get a flavor of just about everything we got going on. Starting with Mercury, we actually have a mission at Mercury right now called MESSENGER, which is a really tortured acronym for Mercury Surface Space Environment Geochemistry and Ranging. I don't know why they didn't just call it MESSENGER. We had to come up with an acronym, but MESSENGER is a fantastic mission. It's been orbiting now for a little over a year. It's our first orbiter to get to orbit around Mercury. Mercury is a really tough place to orbit around because it's so close to the sun. Anything that gets close to it wants to go right into the sun, so there's a lot of very complicated engineering to actually get you into orbit around Mercury without diving straight into the sun. Quick wow fact about Mercury: a day on Mercury is actually longer than a year. Mercury goes around the sun pretty quick. It only takes 88 days to go around the sun, but a single day actually takes 176 Earth days to rotate on its axis, which is kind of cool. It means that one side of Mercury is always very, very hot and one side is always very, very cold. So Mercury, I think, is kind of cool because up until Messenger got there, we just didn't know like anything about it. We had flown by a couple of times in the 70s. We'd only really seen like 40% of Mercury. So this was the map of Mercury until just about a year or so ago, and literally half of it was blank. And we had at graduate school, in our library, we had a set of the globes of all the different planets, and Mercury's always made me so sad because it was literally just blank on one side. So we have finally fixed that. We now have seen all of Mercury. This is the latest mosaic they've put together. We've seen the entire planet. It's a beautiful planet. You can look up close. It's very heavily cratered. In some ways, it looks a lot like the moon, but the more we study it, it turns out the less and less like the moon it is. A quick note about nomenclature. Nomenclature is the way that we name things on planets, right? And every planet, every moon, every asteroid has its own rules for how we name things. So, for instance, on the moon, all of the craters are named after scientists, right? But on Mercury, Mercury is my very favorite naming scheme. On Mercury, all of the craters are named after artists. Artists, musicians, authors. It's really fun. And because we are now just seeing for the first time so much of Mercury, we're getting to name a lot of new craters, right? So just recently, in the last couple of months, we've gotten a couple of new ones. So Andy Warhol now has a crater. Dr. Seuss has his own crater. I love this planet. Someday, I hope, I'm a bit of a painter in my spare time, and it is my dream to one day get my own crater on Mercury. But you have to be dead first. That is one of the rules. You can't have a crater while you're still alive. So I've got a few years to build up my painting repertoire so that I can get a crater on Mercury. Hopefully they won't all be named by then. Talk a little bit about some of the results of Messenger. Like I said, even though Mercury looks a lot like the moon, it turns out it's really not at all. I've put some spectra out here. I don't want anybody to wig out because I put squiggly lines on here. People tend to do that. But the spectra are actually the best way that we can find out the mineralogy of a planet. So different minerals, and these are a bunch of different minerals that we find on the moon, have sort of characteristic shapes to their spectra. These wiggle in very characteristic ways depending on the mineral structure of various minerals. And on the moon, we can use those to figure out what different minerals are present and in what amounts. Unfortunately, this doesn't work on Mercury. This is what the spectra of Mercury look like. There aren't any squiggles. The reason for that is that these squiggles in general are produced because of the way that iron interacts inside the structure of the mineral, interacts with light. And on Mercury, apparently, there's really not that much iron at the surface. And so we get no squiggly lines, which makes it really difficult to tell what the minerals are. We've been there for over a year now. I still can't tell you what the minerals are at the surface. But we're working on other ways. We've got other instruments that are measuring the chemistry, and so from the chemistry we can start to narrow down what the minerals are there, but it's going to be a long process. It's not easy. Mercury is not giving up its secrets quite so freely, but what we can tell you is that it's really not a slightly bigger version of the moon. It's definitely got its own weird, wonderful mysteries that we are still trying to work out. Okay, moving on to Venus. Venus, one of my least favorite planets. We're not going to spend a whole lot of time on Venus. We also don't have, NASA doesn't have any missions at Venus right now. We actually haven't been to Venus in quite a while, but the Europeans do. The ESA mission, Venus Express, has been in orbit since 2006. It's doing some really cool long-term atmospheric studies. Long-term studies are not sort of gee whiz science that necessarily produce new press releases every week, but it's doing some really important fundamental work to try and understand how climate changes over time and weather patterns and things on Venus. The other mission I was going to mention is the Akusaki mission, which is a JAXA. It's a Japanese mission that launched in 2010, but unfortunately, it actually missed Venus. They did their burn to get into orbit, and there was a problem with their burn. It didn't burn completely, and so they actually weren't able to get into orbit. So they're now orbiting around the sun. They're going to come back around to Venus in 2015, and they're going to try again. But whatever was wrong with the burn the first time is likely to still be wrong, and so it's not terribly clear that they're going to be able to make it. But I wish them luck. They're going to at least try again in 2015. Like I said, we hadn't been to Venus in a while, but Venus is actually the very first place we went. When we had our first planetary mission, our first venture out into the solar system, first time we got data back that didn't come from the back end of a telescope was Mariner 2, which went to Venus December 14th, 1962, which, if you can do some quick math, is about a week shy of the 50th anniversary. So we are actually celebrating here in the Planetary Division our 50th anniversary of solar system exploration. There's a handy-dandy website if you want to go and look up some of the activities that we have planned for our 50th year. But it's very exciting for all of us. And interestingly, one of the things that Mariner 2 discovered 50 years ago is the coolest thing, that Venus actually rotates backwards. All of the other planets in our solar system, including Earth, we all rotate counterclockwise. And Venus orbits the Sun counterclockwise, but it rotates clockwise, which is really weird. Our best guess for this is that at some point late, the very last big impact that hit Venus pushed it in the other direction, gave it angular momentum moving the other way, so it now rotates the other way. It rotates really slowly, but it does actually rotate backwards. Super cool. Okay, so after Venus comes Earth, and I'm not here to talk about the Earth. You picked the wrong person to talk about the Earth. Earth is cool and all, but it's not nearly as cool as the other planets. So I'm going to spend some time talking about my favorite little companion to the Earth. That would be the Moon. These, by the way, are actually to scale, just in case you're wondering how far the Earth is from the Moon. I heart the Moon. So the Moon is my bread and butter. The Moon, most of my research is on the Moon. I really, really love the Moon, and so we're going to spend a fair amount of time talking about the Moon so that you all can love it as much as I do. Okay, quick poll. Can we get one of the moderators to put a poll up? Thank you. So, how many spacecraft, does anybody know, how many spacecraft does NASA have around the Moon right now?
And it looks like folks are jumping on that poll question, Sarah, but for those who joined us a little bit late, if you're not sure where those poll buttons are located, they're right under your own name at the top of the participants window. So do go ahead and submit your response, and there's just a few moments here. Oh dear, look at that. I put up the wrong, okay, everybody pause for just a moment. We'll get that D up there. Thanks, Andrew. Here we go, okay. All right, now you can pick A through D. And we'll give a few more moments for everyone to get their answer in there. You guys are very quick. Thank you so much for your responses on this. Looks like most folks are already in there. And I'm glad I got D up because
yeah,
a good portion of folks picked that one. All right, so we'll go ahead and lock our responses here and check out the graph. And back to you, Sarah.
Look at that. I'm actually impressed. We actually have 5 spacecraft in orbit around the Moon right now, which is sort of incredible. So we've got the Lunar Reconnaissance Orbiter. I imagine that most of you have heard at least of LRO. It's been in orbit since 2009. We've got GRAIL, the GRAIL mission, which actually consists of 2 little tiny spacecraft that are measuring the gravity. And then there's Artemis, which is the one most of you have probably never heard of. Artemis is an extended mission from a heliophysics mission called Ceres, which was studying the Sun. So it had actually 5 spacecraft, and 2 of those were then moved out to the Moon and out studying how the Moon interacts with the Sun, which is a little outside of the scope of my knowledge, so I'm not going to talk too much about Artemis, but it is actually making some cool discoveries. If you're interested, you can Google it. So my point here is that NASA is in fact still studying the Moon. I keep hearing, people tell people I study the Moon, and they're like, "Oh, aren't you sad that NASA's abandoned the Moon?" And I'm like, "Are you kidding? This is the most exciting time in lunar science since Apollo. We've not abandoned the Moon. We are doing some incredible studies on the Moon." So I'm going to talk a little bit about water on the Moon. So I've got another poll up here. Can you guys tell me which spacecraft do you think was the first to find water on the Moon? And your poll buttons are now active, and I've got all of those answers up there, A through D.
So we look forward to seeing what you think. And we'll go ahead and lock our responses here in just another few seconds so we can keep moving right along. It looks like most folks have submitted an answer. I'll go ahead and lock that and put our graph up.
Ah, interesting. So apparently nobody's heard of Chandrayaan-1, probably. And it's pretty well split between the other ones. This is kind of a trick question because the truth is that any one of those could be correct depending on your definition of first and your definition of water. So we're going to talk a little bit about what we mean when we say water on the moon. It's actually a complicated story. Turns out there are at least 3 distinct types of water on the moon. I used to complain when I was in grad school about how, it seemed like every other week there was a press release coming out that they'd found water on Mars. I'm like, you found water on Mars again? You found water on Mars again? And then all of a sudden, in like 2008, 2009, it was like every other week there was a new press release that we found water on the moon, and then I was a little sheepish. I was like, well, I guess we do it too. We can't blame the Martian. That's right. So we have in fact found water, distinct types of water in 3 different places. So there is the permanently shadowed region at the poles. It's probably the most common type that people have heard of. There's also this what is called the widespread surficial water, sort of a more esoteric type of water. We'll talk a little bit about that. Made big news in 2009. And then finally, there's water in the lunar interior that was discovered from the lunar samples. And it was discovered just recently, actually, 2008, from samples that were brought back during Apollo. So we'll talk about all 3 in turn, starting with the water at the poles. So the very first one, so you guys who said Lunar Prospector were not wrong. In 1998, Lunar Prospector found hydrogen concentration at the poles. It's these sort of purpley areas at the poles here. Prospector wasn't designed to see water. All it could sense was hydrogen. So we saw hydrogen there, and we thought, well, it's probably water, but you don't know. Maybe it's just hydrogen. We weren't sure what state it was in. So we had to wait a few years until we could finally send LCROSS. LCROSS is a cool little mission that was launched along with LRO. So you can see here is LRO inside the rocket. This is the cutaway version inside the rocket. Here's LRO. Here's the rocket down below. In between it, the way you connect the rocket to LRO is with this little ring connector. And so somebody came up with this really bright idea to actually build a spacecraft out of this ring connector. So they took the ring and they put solar panels on it. They put little jets so they could control it, and they put all sorts of sensors on one side. And then they launched it along with LRO. LRO separated and went off to the moon on its own. LCROSS would normally, you would dump this empty rocket, as once all the rocket fuel was gone, you would just dump the empty rocket, but instead they hung on to it, carried it with them all the way to the moon, and then headed right into the poles here, to this crater Cabeus, which is one of these permanently shadowed regions that never sees sunlight, gets super cold. And just separated just a couple minutes before they hit the ground, they separated. So the rocket went in first, created this big huge plume of dust and vapor and whatever else. And then the little shepherding spacecraft flew right through that plume and then impacted itself. And we found actual physical evidence of water. Okay, so I'm going to put up some more squiggly lines. Nobody freak out about the squiggly lines. Okay, so here in this graph shows you what you're looking for is this OH emission, right? OH hydroxyl is not quite the same as water, but it's one hydrogen instead of 2. And you can see the peak here show up. This is time after impact, so this is before impact, and that peak doesn't exist. And then as you go after impact, you see it start to grow a little bit. And if you follow it along, here's before impact, it doesn't exist, right? And here's the strength of that band over time. You can see it grow, and then the spacecraft crashes in, and we don't get any more data after that. So that was our first evidence. Next slide here, we have a different instrument on LCROSS. This is the spectra from that one. The spectra, the actual data is in black, and on top of that, you have a model fit of what water vapor and ice looks like. And you can see that it fits really good in these various parts where the water vapor and ice should be. But then there's other parts that doesn't fit the spectra, right? And that's because there's other things in there. It turns out these traps are so cold that it's not just water that's getting trapped in there, but pretty much anything that makes its way up to the poles gets trapped there, right? So you've got ammonia, you've got CO2, you've got all sorts of other things trapped in here. In fact, it doesn't show up on this graph, but one of the things they found was a lot of mercury. So if you were thinking that, you know, maybe this would be great water for the astronauts to drink, they might want to think twice about that because they'll all have mercury poisoning. Okay, so widespread surficial water. This is the second kind of water. This was first identified by the M-Cube, that's the Moon Mineralogy Mapper instrument on the India's Chandrayaan-1 spacecraft. So Chandrayaan-1 was the first lunar mission. It was the first planetary mission for India. And we had, the M-Cubed was actually a U.S. instrument that we put on the Indian mission. And this is sort of a compilation of some of the data they brought back from it. You can see all of these black holes. This is a place where they didn't get data. Unfortunately, this mission didn't finish the job. It actually ended much earlier than they had planned. They had a lot of problems. It's a big learning curve for India, but give them credit, right? Because remember, I talked about Mariner 2 being NASA's first successful planetary mission. Notice I didn't talk at all about Mariner 1, which blew up on the pad. So you got to give India a lot of credit for getting their first mission actually to its correct destination and actually taking really some fantastic data. So what M-Cubed found was also water. This is, again, more squiggly lines, right? And you can see here is what water looks like, right? This little blue zone here is the same as this blue zone here. That's where we expect water bands to be. And you can see the little bands here, so some of it did in fact have water. It wasn't something we expected to find, and we found it all over the surface, which is weird. So we started thinking about how this works. Now the spectrometer that took that data can only see the very, very uppermost surface. It doesn't see down into the soil at all. It's only seeing what's really right at the surface. So we don't know how deep that water goes, how much is there. But what we think is going on is something like what is circled in red here, which is just that you have a tiny bit of water at the very top. And when I say a tiny bit, I mean a really tiny bit. I'm talking about single layers of molecules. Okay, so I've heard some scientists refer to this stuff as lunar dew, which is a terrible analogy. It's not at all like dew. Like if you put your hand down on dewy grass, it gets wet. If you did that on the moon, it would not be wet. This is individual molecules bouncing around. It's not the kind of water that you would be able to collect and drink. It's more of a scientific curiosity than a possible resource, right? And so what we think is actually happening is that the solar wind spews off hydrogen molecules all the time. So there's just this constant flow of hydrogen heading towards the moon, right? And the rocks at the surface, most of the rocks on the moon, the minerals, contain a lot of oxygen. They're actually like 40% by weight made out of oxygen, right? And so you have all this oxygen sitting at the surface, you have all this hydrogen from the sun, from the solar wind flowing into it, and somehow they're hooking up right at the surface and creating just these few molecules of oxygen and hydroxyl that are floating around. Okay, so the last type of water is the water we found in the interior, and this is actually a really cool story. So this is a big discovery from 2008. A guy named Alberto Saul. Now, Alberto was not a lunar geologist. Alberto is a terrestrial geologist. He had this idea. So in the lunar community, we have known forever that the moon is completely dry, doesn't have any water. That was the story, right? When the first Apollo samples came back, people started looking for water. They found some, but they thought it was all contamination, and then everybody just decided the moon was dry. We all knew that the moon was completely dry. There isn't any water, and everybody sort of stopped looking. But Alberto was not a lunar geologist. He hadn't been indoctrinated into the story that the moon is completely dry. Why would you bother looking? And so he went and looked, right? And with current technology is so much better than the technology that we had back in the 60s, he actually found some. Using an ion probe measurements, he found the stuff, and he went and he announced it, and nobody believed him. They're like, what? We all know that the moon is dry. We don't know what you're talking about. It's clearly contamination. But no, he actually went in, and if you were looking for contamination, right, if you would take one of these little volcanic spheres of glass and cut it in half and looked from the core out to the rim, right, contamination, you would expect to find more water at the rim than in the core, right, because it would be soaking in from the outside. But what he found is actually there's more water at the core, higher levels than out at the rim. It's actually losing water, not gaining it, right? So it's clearly not contamination. He had such great evidence that everybody was like, well, that's really cool, and they started trying it themselves, and it turned out now everybody's finding water. They're finding it not just in glass, but in other minerals too, and it turns out there's water everywhere. And now everybody's like, well, of course there is. We knew that all along. And we're like, no. Nobody believed him 5 years ago. But all of a sudden we're understanding that, in fact, the ancient lunar mantle, so these beads actually come straight out of volcanoes. They get fire fountained up into the air. Lava does, and it cools so fast that it forms these little volcanic beads. So these come straight out of volcanoes. It's telling you what's going on inside the mantle. And we know now that there has to be water inside the mantle, which is really cool. But it does kind of throw a wrench into our ideas about how the moon formed. I'm guessing that most of you have at least heard of the giant impact hypothesis, the idea that something about the size of Mars came in and hit the Earth as it was still forming, kicked off a bunch of stuff. That stuff sort of swirled around and eventually coalesced to form the moon, right? The idea is that this is a very hot and violent process, and any water and other volatile materials would be lost in that process. So that's why we assume that the moon should be dry. This does not destroy that hypothesis. It just means we have to sort of change our thinking a little bit. It's probably true that after this process, more water got added from comets or wetter asteroids. And so we don't need to throw out the baby with the bathwater here, but it does make us sort of hang a question on some of the things that we had taken for granted. And it's really just a great example of why sample return is so important. We just didn't have the tools in the 60s for this kind of analysis. We do now, and 40 years from now, we'll have even better tools. We'll still be learning new things from these samples. Okay, so on to some more current results. So LRO has been cruising around the moon for a couple of years now, and it's been taking just some amazing imagery. This is acronym crazy. This is the Lunar Reconnaissance Orbiter, Lunar Reconnaissance Orbiter Camera, Wide Angle Camera Imagery, or the LROC WAC imagery. You can see it's really some beautiful imagery they've taken of the moon. And below that is the matching topography, the Lunar Orbiter Laser Altimeter topography of the near side and the far side. Looking at it, I think it's really cool to see how different the near side and the far side are, especially in the topography. You can see the far side has much higher mountains, but it also has the lowest valleys. So you can all see this big purple area here is actually a really huge impact crater, something called the South Pole Aitken Basin, which stands out like a sore thumb in the topography, but you can just barely make it out in imagery. It's one of the biggest basins in the solar system, actually. Some of the other cameras, there's the wide-angle camera on LRO, but there's also the narrow-angle camera, the NAC images. And the NAC images take super high-resolution images. And some of the coolest ones they've taken are of the Apollo landing sites. You can go online and see all of them, but I was going to put up the 12 here because it is my favorite. So you can actually see here is the descent stage. You can see footprints. You may remember Apollo 12 was designed to land next to Surveyor 3. Surveyor 3 was an earlier spacecraft that was set down, and I actually walked over to it and checked it out. So we have the actual picture that they took when they walked from the Intrepid over to the Surveyor. Here's the picture looking back at the Intrepid. It's just amazing to me, right? And the resolution of these things is so good that you can actually see the flags. This is actually the shadow of the flag that they planted there, which is just incredible. So I do recommend you go online and find the rest of these too. They're all just this amazing. So the next time somebody asks you, did we go to the moon? You can go, yes, we have proof. And so are all the other images. So the NAC imager has just been taking spectacular image after spectacular image. There's no way to show even a tenth of billionth of what they've taken. We actually now have more data from LRO, actually several times more data from LRO than from all other planetary missions we've ever sent anywhere combined. We have just huge amounts of data, and nobody can keep up with it. So I invite you to go to the LROC homepage and check out some of these images. I left you the website there, but you can also just Google LROC. And also, if you're interested in helping, we have so many images that the scientists can't keep up. So there's a citizen science project called MoonZoo. Has anybody heard of MoonZoo? Just out of curiosity? No? Yes? No? MoonZoo is a, oh, hey, excellent. MoonZoo is a relative of Galaxy Zoo, if you've heard of Galaxy Zoo. But it's actually a citizen science project where you can go in and actually look at some of these images for the scientists. You can do some crater counting things. You can identify interesting structures in them and other things to alert the scientists that, hey, this is an important picture to look at. It's actually a really cool project if you've got some free time. I went there once to check it out, and I ended up staying for like 4 hours. I couldn't break myself away, so it is a little addictive. Grail. So Grail is just finishing up its mission. You should, as I say here, say a fond farewell to ebb and flow. I think it is today that marks the official end of their science mission. It may have gotten moved a couple days, but I think it's like 2 weeks from today. They will actually be crashing into the moon. They're not going to make a huge splash. They're pretty small. They're both about the size of like a dorm refrigerator, so they're not going to make huge craters. But they have reached the end of their mission, and it was a fantastic mission. This is what the gravity map of the moon looked like before Grail. And this is after just 1 month. Grail's been up there almost a full year now. So we'll see their final data set will be even better than this. But I mean, just the amazing difference that they have done in that time. And they've discovered all sorts of interesting things about the interior structure of the moon. It's a really cool project. Finally, okay, and I've got a little video. How are we doing on time? We're doing okay on time. Okay, so this is the one upcoming mission we have for the moon, which is the LADEE mission, the Lunar Atmosphere Environment Explorer. One cool thing about this mission is that it's actually launching in August, and it's launching from Wallops Island. We're not launching it from Kennedy. We're launching it out of Virginia. So those of you on the eastern seaboard there, keep your eyes out. You actually ought to be able to see it launch. Even if you don't come to Wallops Island, most of the eastern seaboard ought to be able to actually see it launch. If it launches at night and the skies are clear, you should be able to see it for quite a ways. So it's a big deal for Wallops. It's the first time that they are launching something that's going elsewhere. They've launched things to orbit before, but they've never launched anything out into the solar system before. So it's kind of cool. The goal of LADEE is to characterize the exosphere and the dust environment at the moon. And I've become a really big fan of this particular mission because I just became the program scientist just a couple weeks ago. I became the program scientist for this mission, which means I'm the person at headquarters in charge of making sure that the science for this mission actually happens. Whoever the moderator is, can you push the video?
Sure thing, everyone. You'll see a separate window opening up here in just a moment, and I'll also paste the link there in the chat window for you to access.
All right, so is everybody back? Hopefully everybody's back. And we're finishing up with the moon. So just a last comment that there are plenty of other potential upcoming lunar missions. It's not just the U.S. The whole world is excited about the moon right now. So everything from Google Lunar X Prize, which is sort of, if you haven't heard of it, the follow-on to the Ansari X Prize, is Google sponsoring an X Prize to put a rover on the moon. And there's 30-some teams that have lots of really interesting concepts for rovers, some of which are likely going to launch in the next couple of years to try to get to the moon to win a $30 million prize if they manage to get to the moon and rove and send back images. And there's like various things they need to accomplish to get the money. It's pretty cool. China has plans for the moon. They are in the midst of working on a robotic lander. They also have their eyes on sending humans to the moon at some point, but I think that's still a ways out. But the robotic lander is really in the works. Russia and India are collaborating on a lander/orbiter mission called Lunar Glob. And Japan also in the act. They are working on Selene 2. They're having some money trouble, so that one might be still a little ways out, but it does seem the whole world is kind of excited about the moon right now, so I think that we're going to be seeing lots of things landing on the moon soon, which is actually one of the reasons that we're sending LADEE now, because it turns out the lunar environment is so delicate that when you land things on the moon, it stirs up the atmosphere to the degree that it takes months even for it to settle back to normal again. So it's a good time to send LADEE now before the sort of onslaught of all these missions start landing on the moon and messing up the atmosphere. Okay, so quick break for questions. If you have any questions to this point, please
go ahead and type those into the chat, Andrew. And Sarah, we've got one that Leslie had asked earlier. Other than in your PowerPoint here, are the images available to use in the classroom?
Should be. I took most of them from the web, so they shouldn't be hard to get hold of.
Great, thanks, Sarah. And Elena had asked just a minute ago, she was wondering, can students tweet with the LADEE mission?
Yes, LADEE does have a tweet. It's called, I think it is NASA. Wait, is it LADEE _ NASA? NASA _ LADEE. Oh, I should know that. I'm sure if you search Twitter for LADEE, you'll find it. LADEE. They've not been terribly active, but as we get closer and closer to launch, they will get more active. So we are happy to have you.
Great, thank you. Looks like we've got one from Jim. He wants to know electrical charge buildup between light and dark side of the moon. What is the cause? Is there any lightning?
We have not seen lightning, but yeah, we have UV from the sun giving the positive charge on the day side, and I forget what happens on the night side that makes it negative. It's a breakdown of something. I'm not an expert on the electrical charges on the moon, but it is really interesting to think about, that interface where you're going from day to night and what's happening there, and even between shadows and not shadows. It's an interesting, tricky thing for for when we have humans there. You know, the Apollo astronauts were all there during the daytime. We've not really had to contend with nighttime issues, but there's some interesting charging problems there that we're going to have to work out so that they don't, you know, touch something metal and fry their suits.
So we've got one from Carlos. He wants to know, are scientists considering a new moon formation theory?
No, we're still sticking with the giant impact theory. That is still the best thing we've got going. There are those that don't believe it. Jack Schmitt, the Apollo astronaut, being one of the most vocal ones. But you know, it's much like climate change. Like 98% of us are all on board with the giant impact theory. There's still some details to work out, but we still think that is the correct theory in general. It's just the devil in the details to figure out some of these quirks.
Great. And Sarah, let's take one more question. Andrew says he read that the Messenger probe recently found water and maybe organic compounds on Mercury. Also that the Curiosity probe may have found organic compounds. What is NASA planning now that these have been found?
Yeah, so the Messenger, I know, it's exciting science just the last couple days, right? So Messenger did found water and probably some organic-y stuff on Mercury. An important note that organic doesn't mean life. Organic means molecules that contain carbon, which is an important thing. These are not signs of life on Mercury. There's no life on Mercury, I promise you that. But yeah, we did find that just like the moon has those permanently shadowed regions at the poles, Mercury also is not tilted, just like the moon is not tilted, and so it has these permanently shadowed regions at the poles where stuff gets stuck. It's just so cold there all the time that anything that bounces into those traps gets stuck there. And so yeah, we found definitive evidence now that there's water and organic compounds on Mercury. We're not planning on any trips to go back to Mercury to investigate it at this point, but it's still cool. The Curiosity probe, also, if anybody caught the press conference today, yes, they may or may not have found organic compounds. They're still hedging their bets. They think it might still be contamination from Earth, so they're working hard to try and run that down and make sure that what they're seeing is actually from Mars and not from Earth. If it is, that's really cool, but again, this is not life. This is just organics. And not totally unexpected. But really good news. I think that the important news, most important things that came out of the press conference today is that their instruments are in fact working. It is a very complicated spacecraft, and we'll get to Mars in just a second here and talk a little bit more about Curiosity. But I think that the most exciting thing they had to say was that everything on the spacecraft is actually working, and they're getting good data. So where they go with that, well, we'll have to see. That's going to be a long mission. They've got a lot of work ahead of them still.
Awesome. Thank you, Sarah. And now on to the second half of the presentation.
All right. And up next is Mars, in fact, so it's a great lead-in. Mars is very, very busy. I almost didn't have enough room on this slide to include all of the missions we got going at Mars right now. So we actually have missions that have been up there a while. So we've got Mars Odyssey, which has been in orbit for more than a decade. It's the longest-lived Mars orbiter. We've got Mars Express, which is a European mission that we are cooperating with. It's been up there for almost a decade now. The MER rovers, of course, they are not the first Mercury orbiter. I apologize for the typo, copy-paste error. Mars Reconnaissance Orbiter, which is the way we're mostly communicating with Mars Science Lab. It's been up there for quite a few years now, getting a little bit gray. And then, of course, MSL, which I hope you all watched land, was really exciting in August, was it not? And it is by far the most sophisticated rover anybody has ever launched anywhere. It is a really technological wonder, that thing. So here's a little Mars rover family portrait to give you an idea of where we've come from. I don't know if I'm the only one on line who remembers the Mars Pathfinder rover, 1997, which landed on 4th of July. I remember because I was actually a summer intern at NASA down at Johnson Space Center at the time. And I remember one of the scientists had a pool party for 4th of July, and I was amazed because all of the scientists were all out hanging out by the pool, and all of the interns were huddled together in the living room, like desperately watching the landing for any news. And it was very exciting for us, and we didn't really understand what they were doing out at the pool. And then we followed that up with the Mars exploration rovers, which are, unbelievable. and still going, at least Opportunity still going today, doing still incredible science after all this time. And now finally we've got the big guy, Curiosity, which I think it's really funny how sort of awkward Curiosity looks in this picture, with his giant arm hanging out, and he looks sort of like funny on the cement steps, but you know, in his element on Mars, this is a fantastic picture. He looks so at home, right? Here he is on Mars. This is such a great image. I love that he can take a picture of himself on Mars. And you can see right here next to his feet are actually where they took the samples that they were talking about at the press conference today that they may or may not have found organics in. These are the first ones that they've actually fed through the whole system and gotten results on all of the different instruments. It does look like 25, I have to agree. So here's a great, what's been deemed the crime scene photo of the landing of Curiosity. Here's where Curiosity landed, and the other bits of itself that came off the sky crane, the back shell, and parachute, the heat shield, as it was coming down. But what I want you guys to look at in this picture is not those things, but it's actually the geology of the scene. Can you guys see that there are actually 3 different geological units here, right? So you can see the unit that Curiosity landed on here, right? And then there's this sort of brighter unit right here, and there's a third unit down here in the corner that's sort of more heavily cratered. It's got a lot of craters on it. It's probably an older unit, right? So there's 3 different units. So if you were the geologist and had to decide where Curiosity was going to go next, right? Where is the place that you would go? Yeah, it's going to be right here where those 3 units come together, right? So you can see what all of those 3 different units are, and yeah, exactly, and you can tell which one is older, which one is younger, how they intersect with each other, right? And so, of course, there's a lot of very smart people working on this mission. So, of course, that's exactly where they are headed, right? They've named this sort of area Glenelg. Don't ask me how they came up with that name, but they were very happy that it spells its name backwards and forwards. Otherwise, I'm not sure how they came up with that. But there is actually a place in, I think, Scotland or Wales that's called Glenelg, a tiny little town. So they're very excited about the name. And this slide, of course, is already out of date. This is where they were on Sol 50. So they came out from the landing and marched along for a while. They got to about here on Sol 55, and then they stayed there for 40 days. Scottish, thank you. 40 days and 40 nights. Or 40 sols and 40 nights. They stayed right there. That's where the self-portrait was taken. That's where the samples that they ran through the whole system were taken. So they took a long time to stop right just short of that intersection. They stopped and took some time to do some science, but they have actually started moving again. So they're moving their way along, and they should be to this little point at Glenelg pretty soon, actually. But of course, that's not their final destination, right? So this is a fantastic image of Mount Sharp, which is the inside the crater that they landed in. It's the central peak, right? And it's, I mean, honest to God, this photograph is just so gorgeous. And to give you a little sense of scale, that little dot there is about the size of Curiosity, right? So this is going to be a long journey for Curiosity, like I said. We have time though. This is a nuclear-powered rover, right? So we don't have to worry about, like we did with the smaller rovers, about their solar panels, right? We don't have to wait for a dust storm to clear off the solar panels. We don't have to hunker down over winter because there's not enough sunlight. This guy can go and go and go because he's got all the power in the world, nuclear-powered. So this is actually one of my favorite parts of MSL. I don't study Mars, but so the science to me is cool and all, but not really my science. But this is my favorite new thing to tell people when they tell us, why are we wasting taxpayer money on Mars when we could be, you know, helping people in Africa? And it turns out that MSL is actually helping people in Africa. So it's one of the instruments built for the Mars Science Laboratory, ChemMin, is actually being adapted to identify counterfeit malaria drugs in developing nations, which is like the coolest thing ever. So the way this works is that instrument is a XRD, an X-ray diffraction device, which tells you what minerals are in something, right? And usually in a laboratory, it looks kind of like this, right? Which is a little big, to be carrying around with you in the jungles of Africa, right, or onto Mars, right? And so in order to get it onto the rover, they had to miniaturize it. So they miniaturized it down into a tiny little package, right, which now fits into a suitcase. So you can carry the suitcase with you wherever you're going in Africa or wherever else. It turns out that not only malaria drugs, but there's lots of applications for this thing. One of my favorites here is this guy inside of King Tut's tomb using a different version of this same instrument to look at what the pigments are in the walls of King Tut's tomb. How very cool. So, and we got more stuff going on Mars too. People are always talking again about how, oh, we've destroyed the Mars program, we're ending Mars exploration, and that's not true either. We actually have 2 fantastic missions coming up already that are going to Mars. We've got next year, we have MAVEN, the Mars Atmosphere and Volatile Evolution mission, which will launch, yeah, like I said, late next year and study the atmosphere and climate history of Mars. We also have a lander that was just selected a couple months ago, which is another tortured acronym, the Interior Exploration Using Seismic Investigations, Geodesy, and Heat Transport. Say that 3 times fast. InSight, which will launch in 2016, and is actually a seismometer. And there's a heat flow probe and some other things to study Mars' interior, but it will be our first seismometer on Mars, which is cool. Unfortunately, it would be better if we had, you know, a whole bunch of seismometers spread across the surface of Mars, but we're gonna start with one that will give us a lot more information than we have now. So it's a good place to start. Okay, moving out just slightly further into the solar system, into the asteroid belt, we've got the Dawn mission, which just left Vesta, arrives at Ceres in 2015. So it's actually visiting 2 different asteroids. It's the first spacecraft to be able to do that. It can do that because it's using an ion engine, which is a new kind of engine that uses very low amounts of propellant. It uses like individual ions, one at a time. But it means it's very slow, which is why, you know, it took us like 3 years to get out to Vesta, and just to get from Vesta to Ceres, it's going to take us another 3 years almost. So it's slow. So it's the turtle, right? It's slow but steady. Gets you to the end of the race, right? Just a little bit of scale to show you how big Vesta and Ceres are. Ceres is our biggest asteroid that we know of in the asteroid belt. Vesta is also good size compared to most of the other asteroids in the belt. So these are sort of small planetary bodies. They're not little hunks of rock. They're actually full planetary bodies. So another poll question, quick for you, if we can get another poll up. So we talked about the nomenclature on Mercury, right? Vesta, of course, has its own nomenclature scheme. Can anybody guess what the nomenclature scheme for craters on Vesta might be?
Okay, everyone, the poll buttons are now open. You can select A through D. And I see a few people have jumped on that. Please do go ahead and select an answer there at the top using the poll buttons so we can see your answers in the total there. If you've typed in the chat, do go ahead and select an answer on the poll buttons. All right, I see most folks have selected an answer here, so I'll go ahead and lock that and put our poll up, our graph of responses.
So we got pretty much even answers for A and B and a few for C and D, interestingly enough. So the correct answer is B. The craters on Vesta are named after Vestal virgins. There's a slight problem with that in that we only know the names of like a dozen Vestal virgins, and there's clearly more craters than that on Vesta. So they've sort of expanded it to other famous Roman women to ease up on that restriction a little bit. Other features on Vesta are actually named after Roman festivals. That was also a good guess. Things like mountains and hills and other features, scarps, are named after Roman festivals. The other ones, let's see, mythological and legendary names of an erotic nature. That actually is a naming scheme, but that's the naming scheme for Eros, which is sort of makes sense. And as is D, spas of the world. Yes, spas and vacation resorts of the world is actually the name, the nomenclature for, I think that is Gaspra, which is one of the other main belt asteroids. So it's fascinating to see how they come up with these naming schemes. There's another one that's coal fields of the world, just in case you are interested in what the coal fields of the world are. So these are fascinating. I don't quite understand how they come up with these names, but it is always interesting. So here's what Vesta looks like. I put up this this top image because just to highlight the difficulties when you start mapping irregular bodies. So it's hard enough, you know, when you take a round body and flatten it out into a rectangle. But what do you do when you have something that's shaped, you know, like a weird potato, and you flatten it out? You end up with some strange stuff going on around the poles. But it is cool to see it, and I wanted to point out these interesting stripes that go sort of all the way around the middle of the planet, and you can see them here as well, and they go right up here. These things are actually related to these giant impact basins on the bottom, right? So we have known even from Hubble imagery, he's got this weird point at the bottom of Vesta. We could see that even from Hubble. And we've always suspected that that was, in fact, a giant impact crater. So we turn it on its end. So this is this point here, is this point here. This point here is this point here. So we're looking now at the pole, the south pole of Vesta. And you can see in the topography that there is, in fact, a giant impact crater here. And it turns out these stripes actually ring that crater. And what happened was when this thing came in and impacted it, it sort of shoved the whole planet sideways to the point where it sort of wrinkled like an accordion and created these lines that go all the way around. But as they started mapping them out, they found out that they didn't all circle around this big basin. The basin is called Rhea Silvia. Point of trivia, Rhea Silvia was the mother of Romulus and Remus, so therefore a very famous Roman woman. But it turned out that these stripes didn't all circle around this crater, and they found out that there was, in fact, another crater here. So there's two sets of these stripes, one that circles this older crater, one that circles Rhea Silvia. The older crater is called Venenia. Venenia was one of the original 4 Vestal virgins, or so Wikipedia tells me. But you can see it's sort of it's there, but it's much harder to see in the topography. It's actually a much older crater, but it's really impressive that these two enormous impacts happened almost practically on top of each other, but like 1 billion years apart. Really amazing. I don't know what is attracting things to the south pole of Vesta, but kind of cool. We do see some great mineralogical and chemical variations across Vesta's surface, so that impact at the bottom, I actually am not sure what, I didn't put up what this color scheme means, but you can see that where that impact is at the bottom is sort of a different shade. There's a lot more sort of greeny and yellowy colors in that impact around where that Rhea Silvia basin is, right? And the reason for that is because Vesta is actually big enough that it is a differentiated body. Like the Earth, it's got a core, a mantle, and a crust, and that and this impact was actually so big that it actually went down through the crust and into the mantle and tapped into some different mineralogical features. And so you can actually see that in this map. There's also these weird red spots. I'm not sure what the mineralogy of those is, but these probably represent places where big asteroids of a different composition came in and impacted and left behind a lot of material of a different composition. This other map is actually a hydrogen map. We don't have permanently shadowed craters on Vesta. It doesn't quite, but it is far enough away that it's pretty cold there. And it turns out, whatever these things are that are hitting it, some of them were wet, and so you actually can retain water from either those are comets or hydrated asteroids that hit it, and some of that water gets left behind and saved. It's actually pretty stable because it's actually just cold enough on Vesta. We do have one mission that is headed out to the asteroid belt. It was actually just selected about 5 or 6 months ago, called OSIRIS-REx. It's going to launch in 2016, and it's actually going to bring home a sample from an asteroid. An asteroid right now that is called RQ-36, I think, but there was just a naming contest. I think it ended like yesterday to see if we can pick out a better name for the asteroid that OSIRIS-REx is headed to. But that's going to be a really cool mission. first time that we were bringing back a sample return. And we know that sample returns, again, very important because we can study them forever, right? Okay, on to Jupiter. Jupiter is our biggest planet. And we actually do have a mission on its way out to Jupiter called Juno, launched last year. Will arrive in 2016. Takes a while to get out to Jupiter. And it will be measuring the atmosphere, the magnetosphere, the gravity. It is actually looking at Jupiter itself, which to me is the least interesting part of Jupiter. I actually prefer the moons. The moons are much cooler. We spent a fair amount of time with the Galileo mission a while back looking at the moons of Jupiter, and these moons are huge, right? I mean, Ganymede is actually bigger than Mercury, in fact, and so they're all little worlds in and of themselves, and it's amazing how different they are. Io has something like 400 active volcanoes on it. It's the most volcanically active place in the solar system. Europa, people talk about finding life on Mars. For my money, if we find life anywhere in the solar system, it's going to be Europa. Europa's got this little icy shell, but underneath it, there is a huge ocean of liquid water that's floating around, and God only knows what is floating around in it. It's going to be really cool. It's unfortunate at the moment we actually have done a lot of studies of missions that we could send to Europa. We know exactly what instruments we want to send. We know what kind of mission we want to send there. We are shovel ready. If only we had the $2 billion to do it, which we don't right now. But when we do, we're going to send some really fantastic missions to Europa. The Europeans are actually planning a mission to Ganymede called JUICE. I forget what the acronym JUICE stands for, but they're going to go and send quite a really interesting mission to Ganymede. We're going to participate in that. We're going to have some instruments on it, but that's mostly a European mission, unfortunately, which will be cool. And I believe that mission actually will at least fly by Europa a couple of times too. So we'll get a little data from both Europa and Ganymede out of that one. Oh, my gee whiz fact for Jupiter. Jupiter's Great Red Spot is actually a giant hurricane. You thought Sandy was big. This hurricane is actually big enough that you can fit two Earths side by side inside of it. And it's been raging literally for hundreds of years. We've been watching it through telescopes for hundreds of years, and it just keeps going and going and going. Fantastic. Okay, Saturn. We do have a fantastic mission at Saturn called Cassini-Huygens. Huygens was the European part of the mission. That was the probe that landed on the moon Titan. Cassini is the NASA part of the mission. It's been orbiting around Saturn since 2004, and it has just really revolutionized our understanding of Saturn and its moons. We've learned all sorts of cool things. This is my very favoriteest picture that Cassini has taken. It is really an incredible picture. This is from the backside of Saturn. So you're seeing the sun eclipsed by Saturn and filtered through the rings, which is just incredibly beautiful. And just when you think it's the coolest thing you've ever seen, you see that little tiny dot over Saturn's left shoulder there. That is actually the Earth. So all of us, every person you've ever met, everything you've ever seen, all exists on that tiny little dot over the shoulder of Saturn's rings there. Here's another really incredible picture. This is a infrared picture of Saturn showing the aurora. So just like our northern lights, Saturn actually has similar processes happening at its poles. I think that's really cool too. Well, again, just like Jupiter, I think some of the most interesting things we've learned about Saturn are actually not about Saturn, but they're about some of the moons. This is my personal favorite moon of Saturn, which is Enceladus. Enceladus actually has volcanoes that spew water. So you can see in this picture of Enceladus these strange little stripe things that scientists call the tiger stripes. And out of these stripes, you actually can see these little jets of water. This is an artist's conception of what it might look like if you were standing on the surface looking at these little volcanoes of water that are throwing up cryovolcanism, which also suggests that like Europa, there's probably liquid water underneath the surface of Enceladus as well. So also an interesting place to go to look for life. There are currently no missions planned for the ice giants, unfortunately. Poor things, a little neglected. The last time they were visited was before the Berlin Wall fell in the 80s. But we do still study them with telescopes. So take a little minute to talk about it. So this is the Voyager 2 image of Uranus, which is like the most boring ice ball on the planet, you think, right? Except we have just recently taken a bunch of images with various telescopes, Hubble and some observatories here on Earth, in various wavelengths, and you can actually see that Uranus is much more interesting than it appears at first glance. There's actually all sorts of very interesting cloud patterns and swirls and things going on that they're just starting to figure out about Uranus. Neptune as well. We have spent some time with Hubble and other telescopes looking at Neptune. Most interesting thing that we found recently is that this dark spot that we all saw in the Voyager images has suddenly disappeared. It's not there anymore. So I don't know what this was to begin with. Presumably some sort of storm, but it apparently has died off and quieted down. So we do have to remember that these things are changing. We would love to send a mission out to the ice giants. It's again not really in the budget cards for a while, but people are starting to think about it, figure out what we would like to do there and when we might be able to get there. So it'll be a while, but we won't forget about them forever. Okay, and out beyond Neptune, we do have one mission that is headed out beyond Neptune. It's New Horizons. It launched, seriously, in 2006. It won't actually get to Pluto until 2015, where it will characterize the geology, chemistry, morphology of Pluto and Charon and all of the other moons of Pluto. It's a really cool mission, but you think about it, it's a flyby mission, right? So the entire data collecting part of the mission is only a couple of hours long. So it took like 10 years to plan this mission and get it launched, and then another 9 years to get it to Pluto, and the whole thing is over in just a couple of hours. So you really hope you have a good day that day and everything goes well. So my question to you all is Pluto a planet? What do you guys think? This seems to be the question that I get asked most often when I go out to talk to people. Everybody seems very upset about Pluto not being a planet. Oh, and I see that you guys also are very upset about it. Depends on the definition. That is an excellent point, Teresa. Dwarf planet, does that still count as planet? Non-circular pattern, it's true Pluto has always been a little weird, right? It's very elliptical in its orbit. It doesn't in the same plane of ecliptic as the rest of the planets. It does, it crosses, actually not, isn't always the furthest planet out. So yeah, so it comes back to the question of, yeah, it hasn't cleared its neighborhood, we'll get to that. It comes back to the question of what is a planet, okay? So in my day, there was sort of a working definition of planet in which it was a body that orbits the sun and is at least 1,000 kilometers in diameter, right? And so that worked because Ceres, like I said, the largest asteroid, right? Ceres is about 950 kilometers in diameter, so it's just under the cutoff. Pluto is well over it, so that worked. But that is a terrible definition, right? Because 1,000 kilometers, that is some random number we picked out of the sky because it worked for what we needed it to work for, right? You don't want to base your definitions on random numbers, okay? You want some sort of real reason to have picked that number. But it was working for us and nobody questioned it, right? Until all of a sudden we started finding other trans-Neptunian objects. Trans-Neptunian, by the way, simply means things that are out further than Neptune. All right. Most notably, we found Eris. This is Eris here in 2005, which is actually bigger than Pluto, right? And suddenly there was a hiccup. Well, what are we going to do? Is Eris a planet? Right? And then we started finding all sorts of other things out there. It turns out that that neighborhood is actually pretty crowded, and we've pretty much been steadily finding these other things that are, you know, of the same size range as Pluto, hanging out there, right? And so it's become a problem and we had to deal with. So in 2006, the International Astronomical Union, which is the same international body that does all of the naming of the craters and other things, right? So there are international the people that we have to listen to so that we don't have enormous confusion about names, right? So, and it's literally just a room full of people, and they took a vote, right? And it was not a unanimous vote by any means. It was actually a pretty close vote that decided what the definition of an orbit was. So the definition is that it has to be in orbit around the sun, right? And it has to have sufficient mass to assume hydrostatic equilibrium, which is a fancy way of saying it has to be sort of roundish, right? And it doesn't have to be perfectly round. Something like Vesta would probably meet this criteria, even though it's a little potato-y shaped and has that pointy end. It's round enough. But the problem is actually this third criterion. It has to have cleared the neighborhood around its orbit. People really didn't like the wording of this, right? Because what exactly does cleared the neighborhood mean, right? And we sort of know what they mean, right? They mean if it's part of an asteroid belt or the Kuiper belt where there's all these little things floating around, and that doesn't count, right? But how about the Earth? Has the Earth cleared its neighborhood? Because we have lots of near-Earth asteroids floating around here too. I mean, it's not the asteroid belt, but there's no shortage of near-Earth asteroids, right? And so what exactly does clear the neighborhood is not very precise language, and people have a real problem with that. So this is sort of where the debate has come. People are not terribly happy with this definition because it's not precise enough to be a good definition. But it is what we have right now. It is passed. It is the law of the land as far as the IAU is concerned, and so we have to go with it until something else happens and we've decided it's not a good enough definition anymore, and we change it. So that's the end of that, right? We all have to get used to the idea that Pluto is not a planet. Those of you who are still against it, I promise you, Pluto is not a planet. But even though we're down to only 8 planets in our solar system, it's actually a really exciting time now for extrasolar planets. We are finding almost 800. We're finding hundreds of extrasolar planets around other suns, including this is an artist's conception of Kepler-11, which is at least 6 planets orbiting around it. The longer we look at some of these stars and see some of these systems, it looks like planetary systems like ours are the norm in the system. Every star we look at seems to have its own little planetary systems around it. Most of these new planets are coming from a mission called Kepler, which is not a planetary mission. It's actually an astrophysics mission, different section of NASA. But we still care because planets are still our domain, even though we're not the ones finding them. Kepler, the way it's looking for planets is by staring at this little field of view. Right? It stares just at this field of view. It's not looking anywhere else in the sky. It's just constantly staring at this same field of view in the sky, and it's looking for dips in the light curves of stars. So every time a planet passes in front of a star, its light curve dips just a little bit, and so you can measure very precisely the output of these stars and see when they dip and how much they dip, and get a feel for what the planets are, how many planets are there. So if you remember the transit of Venus a few months ago, right? This is sort of a similar thing, transit in front of the star, and you can see its light curve dip. And from that, they have tracked a number of candidates. So now they want to wait and measure that same dip repeatedly as the planet goes around the sun multiple times, so that you can be sure that what you're seeing are real planets, right? And you can get their period, how long it takes them to go around the sun. But what we're seeing is it doesn't matter where you look in the sky. There are planets everywhere. Of all different sizes, right? And the longer we look, it's easy to see the big planets. The smaller, the Earth-sized ones are harder to see. We've got to look for longer periods of time. So the longer that Kepler is up there looking, the more and more of the little guys that we're seeing too. We're getting some really amazing statistics on these. And I put up this website here. If you guys are interested in graphing, you can go to exoplanets.org. They've got this cool little thing where you can tell it what parameters, whether it's size or distance from sun or whatever, and it will graph it for you. All of the current data from the ones that they have confirmed among the Kepler exoplanets. So I do recommend going there if you like to play around with graphs. It's kind of a fun little website. So this is I stole this from XKCD. I love this picture. It gives you a real sense of all the planets we've known. So here in this little box is our solar system, right? So you can see Jupiter and Saturn. You can't even see the Earth. We disappear in the noise there. But this is all of the other planets that we found to date. There's a lot of them. And I'd just like to note that I have to agree with XKCD that this is a really exciting time. It's a really exciting time for people to study exoplanets as well as all of the other planets. And that's the end of my presentation, but I am happy to take questions.
Thank you, Sarah. Fantastic. I will, let's see, we're going to take a few questions right now, and just to make sure that we stay on time before our evaluation, I'm going to set a timer here for 3 minutes. And so, folks, if you have questions, feel free to type those in. We will have another period of Q&A after the evaluation as well, so keep that in mind. I don't see any new questions, but I'm going to go back to some that folks typed in earlier. There were a number of questions about Jupiter, and if you've already covered these since then, just let me know. Christy wanted to know how long it would take to get to Jupiter.
Let's see. Well, let's see. Juno launched, like I said, last year, and it will get there in 2016, so it takes about 5 years.
All right, great. And then Lori wanted to know, why are the moons of Jupiter all so different?
That's an excellent question, and one that we are working very hard to figure out. I mean, so part of it is due to how far they are from Jupiter. Like Io, the one that's really volcanically active, is close into Jupiter. It gets pulled tidally by Jupiter, and so all that tidal stretching causes a lot of heat, and that's where all the volcanoes come from. So some of it has to do with their sizes, different sizes. You have different processes going on. Some of it has to do with their composition, how much ice was there, whether you had a lot of water or a lot of rock, what the variations in those are. A lot of it we just don't understand. Those are a lot of still open questions.
Great, so good question there, Lori. It looks like Teresa had another question related to Jupiter. She wanted to know about the spots. She wanted to know, does the hurricane migrate?
Yeah, it moves around. Different. In fact, all of those different bands of clouds on Jupiter, a lot of them are moving at different rates, and so yeah, they sort of wiggle all the way around the planet, much like clouds on Earth do.
Great. And then we had one from John, just typed in a minute ago. He wanted to know, what about Voyager leaving our solar system?
Yeah, Voyager, talk about the mission that just kept going, right? It's actually, we've turned it over. It was, of course, it was a planetary mission when it was going by the planets, but it's now actually a heliophysics mission, and they're still getting really great results. We actually think that we've just passed the heliopause, which is the name for like the edge of the solar system. So, and it's tricky because they don't really know what the edge of the solar system looks like. So they think maybe we've passed it, but we're gonna have to like keep collecting data for a while and then look back and see if we did actually pass out of it or not. In order to, we have to look back in retrospect because it's hard to tell while you're in it whether we've passed it or not. But it's amazing that we are still getting data from that thing. It's been going for years and years, and it now takes, I mean, it's so far out there. It takes something like 45 minutes one way to get data. Like it's incredibly far.
Wonderful. Thank you so much, Sarah. And folks, you probably just heard our 3-minute timer bell, and I want to give everyone a chance to get out of the web seminar on time, but we will have a few extra minutes of informal Q&A with Sarah at the end. So at this point, I would like to thank Sarah Noble, tonight's presenter, and everyone, if you can use that emoticon button to give Sarah a round of applause. We'll show her appreciation. And thank you, everyone, for attending with us tonight. Your participation was fantastic. And of course, we would like to thank the sponsor of tonight's web seminar, NASA. And a thank you to the administration of NSTA for their support for web seminars. Here's a look at what's coming up on the NSTA web seminar calendar. You can join us tomorrow to learn more about preparing for the next generation science standards. This will be the 7th program in our series of 8. We'll be looking at the practice of engaging in argument from evidence. And then on December 5th, you can join us with the American Chemical Society to look at physical changes, chemical changes, and how to tell the difference. And then on December 6th, join us for another program in our NASA Explorer School series, Engineering Design Challenge Thermal Protection System. And you can register by going to learningcenter.nsta.org/webseminars. Thank you, everyone, for your participation tonight, and we do look forward to seeing you again on another NSTA web seminar.